My story actually begins with a marble, a child's toy, right? And it was a seemingly simple task that I set myself, which was to design a marble, explicitly design, using existing tools, CAD software, computer-aided design software, a marble. And so I went about to do this, and actually this has defined a large portion of my life, and I'm going to talk to you about that today, because it wasn't as simple a task as I thought it was going to be. The first thing I need to do is explain to you, give you a little bit of background into my world, because it took me down a rabbit hole, and you need to understand where that rabbit hole kind of leads and where I work. So design applications and software is sort of the first level, the upper level. That's sort of the applications that people use, but also I'm talking about the applications that this software is used for. So we're talking about applications like three-dimensional modeling for animation, like Gollum in Lord of the Rings, or we're talking about 3D printing and additive manufacturing is the sort of technical term for that. And so that's the top layer. But that's all informed by the user interface and how the designer and the person interacts with the user interface. And so it's not working. Let's try again. Okay, there we go. Was that me or you? So graphical user interface, yeah, it obviously causes a lot of issues. So the graphical user interface, along with the designer, sort of informs what is possible in terms of the applications in some sense. And that, in turn, is informed by the actual modeling framework itself. So let's see if this is working. Yes. So the modeling framework itself. So the modeling framework defines what the application on the back end can and can't do, what its functionality is. But that's actually in turn defined by the geometric framework, the geometric kernel. So the geometric kernel is the heart of the whole thing. And that's where I work. So it defines what is possible. And it's actually answering the question, how do you go about, or how to exactly capture and represent physical space and objects. This is actually now, if you're paying attention to what I've been saying, at the very beginning I started out with a very simple task that then became a more complex question that's now become a very serious problem. And this problem is as old as mathematics itself, actually, because geometric kernels are very much related to that. Although in the digital world it's a slightly different story. So let's go back to the task that I set myself. It was to make a marble. Now there's something really interesting about this. The marble is not as simple as it might look at first. There's some interesting properties. This marble actually has a distribution of material inside of it. And it actually has like bubbles, if you can see that. And it's also got chips in the surface. There's actually quite a lot of detail in that marble. And if I were to try to model that in a sort of simplistic way today, I would model that this way. So I'd model that using surfaces, and it would end up looking something like this if I didn't apply a texture map to the outside. So what we do is, for visualization, we trick the audience or the viewer by doing things to these surfaces to make them look real. But in fact, if we go back, the materiality that we see inside the marble, one more back, has very little to do with what we see and forward. I like this. It's a verbal interface. This is Siri. Okay. So you can see there's very little correlation there, and I'm going to give you an illustration of that. So this is just to show you how people model. This is a water bottle, and if I were to model this in a CAD package today, basically what I would do is I'd make all these surfaces and I'd trim them, and I'd bend them in space and orient them such that eventually, if I did it correctly, this bottle would end up being watertight model that was completely defined by all these surfaces. And this is more or less a very good analogy for how modeling is done today. But notice it doesn't define the water inside, there's no volumetric properties to this, it's simply a definition of the surface. And if it has a crack in it somewhere, if I've modeled this incorrectly, this bottle will leak, right? It will run all over the floor. And again, for visualization, not such a big problem. But for manufacturing, for example, big problem. Because what's inside and outside? How do we know how to fill this with material and what kind of material? Sometimes, however, we might want to open it. And it might be good that it leaks. But, so, now you might think this is a mistake, or that a bad programmer was involved here, but actually, this is a larger problem. It's a problem about how we look at reality and how we see things, and how we define the world around us and design. So we've been given a really nice ability, a very powerful ability. It's kept us alive, it's allowed us to identify threats and friends, and that's the ability to look at objects in the world and identify them as separate from everything else. So we define boundaries around things. I can define, for instance, many people in this room, chairs, this clicker in my hand that's not working, and so forth. So, and you see the child there drawing in the sand. This is the sort of classical way that we view things. But nature doesn't do that. Nature sees things as complex and continuous computation. It's constantly interacting. So it sees all this stuff, and as a matter of fact, that's actually probably the valid way to look at things, right? You're breathing air in, you're breathing air out. All the stuff in the room is interacting. So it's not separate, it's all combined. But what we do is we take materials from nature, we simplify them so they fit into this sort of simplified view of things, and we put them back into even natural objects. We make human-made objects that stand apart from nature, but then we even insert them back into natural objects, which arguably maybe isn't the best thing to do, but we've been pretty good at it, actually, up to this point. So why does this matter? Why does everything I'm telling you here matter in terms of the marble? Well, it's because information has changed fundamentally, and it's giving us new capabilities. And so stay with me here, keep what I said, and this will all come back together here in just a minute. So when we look at information, information actually has materiality and always has at any given moment in time. That materiality has changed and the properties of information have changed. So if we look at, for instance, the stone carvings, where we would carve into stone, right, information, writing, it had certain properties. It's hard to move, hard to change, hard to create in the first place. If we look at books, for example, well, everybody knows the story of the printing press. I don't think I need to go into that so much. And if we look at digital silicon, of course, we have some idea there, right? We're starting to move around electrons and photons. And this is actually really important. We're getting closer and closer, but then we hit photons and electrons. We get down to the atomic scale. And it's interesting, we mark history as sort of mastery over different materials. So if we look at, say, the Stone Age, the Bronze Age, and so forth, we call this the atomic age or the age of information. So that's an interesting correlation, right? And so why does it matter so much? Well, it matters because it's a real sort of watershed moment. It's a division line. It's a division line because when you get to this scale, matter takes on completely different properties than it has before. It becomes alive. It is, if you will, an aha moment for information, where information and matter, in some sense, converge. And we have the ability for information to be embedded into anything, for information to be weightless and infinite, and most importantly, information becomes active. It starts doing things. And here's the part where it all comes to a nice neat bow, which is this is what nature already does. Nature doesn't separate information and matter. It's all the same thing. It's all interacting all the time. We've just finally gotten to the same playing field, or at least for us we have. Now there's another nice piece to this, which is we've just now reached a sort of pivotal moment in sort of the digital revolution, if you want, in the age of information, and that's additive manufacturing again, 3D printing. And 3D printing, this is the 3D printer made by Evan Malone and Hod Libson in Cornell. This was the first multi-material printer ever made. It was a DIY printer. You can still buy this, I think. It's similar to the RepRap or the MakerBot, if you know what that is. But this printer was different because it was multi-material. It actually printed a robot with its circuitry, batteries, and everything on the bed of the printer, and the robot was moving before the printer finished. So this means, what does this mean? Well, it's big, right? This means that we can now make stuff at the quality and scale of nature. Okay? So instead of purifying materials, maybe we do, maybe we don't, when we take them from nature, and maybe we use digital computation, maybe we use chemical computation, but now we're talking about mastering control to the point where we can make objects that maybe they're exactly copies of nature, but they don't have to be. But the point is they can integrate with nature. So we start to blend man-made and natural-made objects. But we still have a problem, or we can do that. We still have a problem. And the problem is the information itself. So we're coming back to the marble. The marble is kind of an analogy, if you will. This is a more complex example. This is a watermelon. And if you look at this watermelon, on the left-hand side, you'll see that there's a watermelon modeled in the CAD software. And today in CAD software, that's about, or in design tools, design software, that's about as best as you can do. You could spend some more time and put some structure into it, but it'd be very painful and it'd be very difficult to change afterwards. If you look at the watermelon, the real watermelon, on the right, there's almost no similarity. So we fundamentally have a problem here. We've got the ability to start manufacturing stuff like this, maybe not a watermelon yet, explicitly anyway, but we don't have the information system to do it. So we have to stop thinking, and it's not just a problem of the software again, right? It's a problem of how we approached it. We approached the software that way because that's the way we thought originally. We have a long tradition of drafting, right? And the thickness of a pencil is nothing like the thickness of a line in a computer. In fact, the thickness of a line in a computer can be defined as anything you want. It's the beauty of it. So it's very, very different. So we need to stop thinking of things as boundaries that are drawn in space, and we need to start thinking of things as painting with real materiality, with real substance, volumetrically, right? Very different approach, and we're talking about simulation here too. I'll get into that. So digital materialization is the term that I use to describe this. This really means two-way conversion between matter and information, if you will, or at least maybe matter in different forms. One that's more information friendly, electrons, photons. The other one that is sort of static and you can use. You can pick it up and do stuff with it. So that's sort of the phrase. There's a couple things that are important in order for that to exist. We have to have a system that has the following properties. It has to be symbolic. So that means it has to be similar to the way that we deal with other exact systems like mathematics, or it indeed is mathematics itself. It has to be volumetric. So it can't just be defining a 2.5D, right, a set of surfaces arranged in 3D space. It actually has to define at least 3D space, if not 4D, maybe more dimensions. It has to be constructive. So it needs to be something like Legos. The really important point is here we do work in boundaries. We can't ignore that. So we have to be able to work in chunks. We have to be able to grab stuff and stick it together. There is something called CT scan data, right? Medical data, where you're scanning the body through and through. But that makes a lot of little voxels, a lot of little points in space, and it's very difficult to manipulate. So that's no good. It also has to be continuous. So that means it actually has to have infinite surface, right? You can keep zooming down, you can keep going down to any resolution you want. You shouldn't be limited. And it has to be exact, of course. So the system has to have exact inputs and exact outputs. So myself and a larger team of people have worked for many years on research behind a new approach to geometric modeling. This is the first commercial available package. It's a plugin to a package called Rhinoceros. It's a 3D modeling design package. And it actually allows you to model in the ways that I'm talking about. And if you look at this, the image that you just saw before this was a cube, and you might have thought, okay, well that's a cube and it's got some texture on it, but it's actually not a texture. If you zoom in, you start to find that there's millions of elements in this object. And you can actually go inside the object and there's millions of elements inside of it. And I'll show you a short video just to sort of give you a taste of what that means. This is an element being defined that will then be replicated in space. It doesn't have to be uniform in this case for this example I'm showing that. So you see the cube, you see zooming in, and you can see how massive, right? The number of elements are. This is not currently possible in any other approach using CAD. We can also take that and combine it with sort of traditional shapes and forms. So, for instance, if you had part of a space shell that you were looking at thickening and thinning out for weight constraints and stress, for instance, the bolt hole should be thickened around the microstructure so that it can't break. And also, the really important bit here is that you can thicken the microstructure against the shell. So you can actually blend it continuously, and you'll see that here in just a second, which is the coolest part. So there it is. If we zoom in here, I think in just a second, you'll see the microstructure continuously blending into a solid shell. So again, taking on attributes and sort of kind of approaches that you would see in nature. Here's some of the kinds of structures. This is brand new. It's only been in existence for less than a year. It's only been sort of embraced by a handful of designers so far in some sense. I mean, if we look at the world of design, because we are just scratching the surface, and we're also getting out there to see what people think. But you can sort of take a look at these are some of the outcomes that are coming out of it in terms of some of the shapes. So there's two different things I want to talk about here. There's sort of really, there's a bunch actually. The impacts of this technology and the impacts of digital technology are massive, but I'll discuss two important points related to design in this context. One is that objects become programmable. So we're not talking about, again, storing the data in space. The really important thing to understand here is we're actually capturing the mathematics for the object itself, or the program. So we actually end up with the program of the object directly, which means that you can incorporate simulation as part of the modeling process, and what we call fitness, right? So fitness is where you have a criteria for what the object should meet. For instance, in this case, this is a control arm for a car, and what we wanted to do is we wanted to see that it was 10% lighter while maintaining its strength. And indeed, that was the process. We did achieve that. And you can see that the computer used a lot of different techniques to get there. But this was all closed loop, running through simulation, or nearly. We're still working on some bits there. And you can also see the massive changes that can be made very easily in the system. If you look at the bottom here on the right, the clay images, you'll see sort of the skin can be extended out arbitrarily, just as one example. I also want to talk about something called metamaterials. This is sort of a new word that's a rage. Right now it sort of is referring to making objects invisible. And if you want to talk to me about that later, I can sort of discuss that with you, but it's basically moving electromagnetic waves through a structure so that a small object becomes invisible. But actually metamaterials is a much larger definition than that in my mind. And really what it means is that we're going to be able to take traditional materials. If you were to print a block of it or you were to cast it, it would have a certain attribute. But when it's printed in a different form, a different structure, it takes on a completely different quality. And here you're seeing an object that is completely water resistant or hydrophobic because of the way that it's been made and the materials that it's made from. And so what's really interesting about that is you see the cube, it's completely porous, but yet the water's sitting on top. You see the ball, and the ball is holding fluid. You could put that ball in a vat and swirl it around and pick up fluid. Another attribute is the ability to mimic sort of nature. So this is mimicking bone. Those are oyster shells. The oyster shells have a certain property of flexibility and strength. And so at MIT they just did this, and this is actually at a pretty large scale. You can see it's not even that fine yet. If they print it finer, who knows where we're going. But this is actually larger than 20, this is stronger by 20 times than either of the two material components it's made from. So it's pretty outstanding. I'll skip through this for the most part, but this is a project that we did with Neri Oxman where we were informed it with medical data. I just want to touch on the fact we can bring in medical data directly now and use it in modeling applications. And so we can make very, very complex objects doing that have multi-material properties. At the time this was made, it was maybe the most complex object that we knew of that was explicitly designed. It had flexible material and a hard material. So it took on different material properties at different points in the object. Again, scan data for vascular and bracing, scaffolding for biology, internal vascular systems that we can use directly, and cell simulations. So this is simulating cellular growth because we're actually looking at doing kidneys and vascular trees. So we need to understand how the cells change as they grow, because after you print the cells or arrange the cells, you have to grow them. And then finally, I want to leave you with the notion that we're really heading towards a world where nature, natural-made objects and human-made objects will converge. This is an object that's obviously man-made, but it's solar panels. It collects light during the day, and then at night it lights up. It's a very cute object. The point here is that we're heading towards something I call the physical Turing test, which is where I will put an object on a table. I'll ask you, is it man-made or is it human-made? Is it human-made or is it nature-made? And you might say it's nature-made, and indeed it was human/computationally made. And if that's the case, it passes the test. In fact, I believe that test will probably be passed first before the actual Turing test. If you don't know what the Turing test is, come and talk to me later. I'll explain it. So that's one notion I want to leave you with, is this idea of this physical Turing test and how pivotal that is. I also want to leave you with one other notion, which is, I sort of jokingly, people ask me, well, where's this going? What does that mean? And I say, well, it means that we're talking about something like, taking a forest and turning it into a power grid, right? Taking power directly from photosynthesis right? And that was sort of a ridiculous, sort of out there notion. However, I found now that I can no longer use that as a ridiculous notion because at the University of Georgia, they've actually achieved this. They've taken plant cells and carbon nanotubes and are actually extracting electricity from them. So how far away we are from an actual forest, I don't know, but it's not just fiction. And so the last thing I'd like to leave you with is, if we're really going to embrace the technologies that we've got, this sort of digital world that we've created, these perfect signals that we've developed, and the ability to compute at this really fine scale and move stuff around, then we have to actually think about our design systems and think about the way we think about design in completely different ways. And we have to take that to a level where we're developing tools, volumetric tools, and we're developing tools that can incorporate this data and run simulation against our designs. In some sense, we're looking to, if you will, put digital dirt or dust back into the system. And finally, I would like to say, while we might still be waiting for something to pass the physical Turing test, or we're waiting for a forest as a power grid, that's probably a fair bit away. I'm happy to say I'm content with the fact I am finally able to make a marble.